Now that we've seen something of the construction of a modern motor, let's look at some basic electromagnetic principles to see how they work. Firstly, when a current from a DC supply, such as a battery, flows through a conductor, a magnetic field is formed around that conductor. This can be seen by placing a compass close to a conductor and switching the supply on or off. In this demonstration of a simple motor principle, a conductor is placed at rest in a magnetic field and the current switched on. We can see that the conductor tries to move out of the magnetic field. The direction of this movement is determined by Fleming's left-hand rule. If the first finger is pointed in the direction of the magnetic field and the second in the direction of the current, the thumb indicates the direction of movement. In the same way as a current flowing in a conductor causes it to move out of a magnetic field, moving a conductor in and out of a magnetic field will cause a current to be generated, and Fleming's right-hand rule now applies. Here, if the first finger of the right hand is pointed in the direction of the magnetic flux, with the thumb pointed in the direction of motion of the conductor, the middle finger represents the direction of the generated EMF. The current generated will be determined by the strength of the magnetic field, the rate of movement, and the length of the conductor in the magnetic field, which clearly is greatly increased by forming the conductor into a coil. Here, 3 coils have been mounted on a spindle so that they are free to spin within a magnetic field, and we have a simple DC generator. The current generated in the coils is collected by this switching device called a commutator. If now, instead of spinning the shaft by hand, we supply the coils through the commutator with current from a battery, the little generator immediately becomes a DC motor, because the fields produced by the coils interact with a permanent magnet to cause rotation. We can see from this animation how the direction of this rotation is confirmed by Fleming's left-hand rule. An AC induction motor works on a rather different principle, with the electrical energy supplied to the rotor by induction rather than a commutator. To understand how an induction motor works, we should first look inside a modern power station at the principle behind these massive alternators. The conductors which make up the windings in the stator of this alternator are connected into sets of 3, each set arranged at 120 degrees to each other. When the rotor, which is in effect a giant magnet, is spun by the steam turbine, current is produced in each of the coils in turn, with the current changing direction in each coil once every revolution. From this diagram we can see how the current generated in just one coil rises to a maximum, then decays to 0, before rising to maximum in the opposite direction. Now we can see the effect of including the second and third sets of coils to give us the waveform for a 3-phase supply: the red phase, the yellow phase, and the blue phase. If inside the stator of our motor we arrange sets of coils also at 120 degrees to each other, connection to the 3-phase supply will produce a magnetic north-south field, which will rotate at a sympathetic frequency to the alternator. We can see the arrangement of these coils on a simple diagram. This represents a 3-phase, 2-pole winding in 12 slots, with 2 coils in 4 slots per phase. At time 1, coils in A slots are producing maximum flux. At time 2, coils in B slots. At time 3, the coils in C slots. Then at time 4, coils A again, but this time with the direction of the current, hence magnetic polarity, reversed at position A2. Then at time 5, 6 and 7, it continues with the polarity reversed. Looking now at a rotor, and we can see that the rotor consists of aluminium bars cast into slots connected together with solid end rings. With the rotor stationary, the rotating field moving relative to the rotor cuts through these conductive bars, so inducing large currents into them sufficient to result in a second magnetic field which opposes the relative movement, giving rise to a force or torque on the conductors, which causes the rotor to turn in the direction of the magnetic movement. To determine the direction the motor will turn, we should consider the rotor bars turning counterclockwise in a stationary field. If we apply Fleming's right-hand rule for generators, we can see that the induced voltages in the rotor bars cause currents to flow in the direction indicated. Now we can apply Fleming's left-hand rule for motors. We can see that with the north-south field and currents as shown, the rotor bars will be caused to move in a clockwise direction and so attempt to follow the rotating field. If the rotor is able to turn at the same speed as the rotating magnetic field in the stator, this is known as synchronous speed. However, for other than specially designed motors, known as synchronous motors, the rotor can never reach synchronous speed. The reason for this is that if the rotor bars were moving parallel at the same speed as the stator field, because there would be no relative movement, there would be no EMF induced into the rotor bars to produce a magnetic field, and consequently no torque developed. With standard induction motors, sometimes known as asynchronous motors, the rotor speed is always less than the synchronous speed. The difference between synchronous speed and the actual rotor speed is known as slip. The actual speed of a motor then is determined by the frequency of the supply, the number of pairs of poles, and the degree of slip. For example, if a 4-pole motor is working on 50 Hz, its field speed in revs per second would be determined by this formula. Ns is the synchronous speed, equaling frequency in revs per second over p pairs of poles. Therefore, Ns equals 50 over 2, or 25 revs per second. If the actual rotor speed is 1450 revs per minute, then slip is given by this formula. Ns, the synchronous speed, minus n, the actual speed, over Ns, multiplied by 100. To put the figures in, 25 revs per second equals 1500 RPM. So 1500 minus 1450, the actual speed, multiplied by 100 over 1500, which equals 3.5%. Although the speed of this type of motor is not easily variable, this is possible by either varying the supply frequency using special control gear known as power inverters, or changing the number of poles by using specially designed windings which can be reconnected, usually through a special starter, to provide a different number of poles. This can provide up to 4 different fixed speeds, although no intermediate speeds are available. The 3-phase caged rotor motor is ideal then for drive systems where speed control is not required. But especially in the larger sizes, it does have the disadvantage of fairly high starting currents. And where this is an important factor, or it is necessary to start high inertia loads, wound rotor motors may be specified.